Hi, everybody. Thanks for being here. My name is Pavlo Penenko. I'm a senior software engineer at Maxon, working on Redshift RT, primarily on the HLSL infrastructure of Redshift RT. And today my presentation is Pythonic shader metaprogramming with Metashade. And I'm going to spend the next 10 minutes unpacking this title. So what is Metashade? First of all, it's not officially a Maxon project. I have to say it as a disclaimer. It's a personal project. It's out there on GitHub. And what it is the embedded domain-specific language, which means that it takes a general-purpose programming language, in this case Python, overloads some of its syntax and implements a domain-specific shading language inside of Python. What it can currently do, it can generate a subset of HLSL, but it's definitely designed with more targets in mind. The license is Apache 2.0, very permissive, and meta in the name refers to metaprogramming and not to Meta, the corporation, or the metaverse. And the name actually predates both of those trends. So here's a companion repo to Metashade, the Metashade GLTF demo. It's basically a proof of concept, proving that Metashade can generate shaders that can render something. And it uses AMD's open source Cauldron framework as the C++ host app. And it also uses the third-party PyGLTF lib to load and parse GLTF assets in Python, which is an example of how Metashade can integrate with the wider Python ecosystem and drive shader code gen with the help of that. And what the app does is really just meat and potatoes rasterization. It reimplements the shaders originally written by AMD. And with this, I just wanted to make sure that Metashade can generate the most essential code first. So what does it look like in terms of code? Well, here we have two code snippets, one in Python and another in HLSL. And, well, the Python code generates the HLSL code as it executes, line by line, which is unlike some of the other projects using Python for GPU programming. And as you can see, there is some idiosyncratic syntax on the Python side. I'll go into more detail later why that's necessary. So at this point, some of you may be wondering why we need Metashade, why not use some existing approaches. After all, people have been writing shaders for decades. And I would say that, well, Metashade addresses the same, well, known pain points of shader programming, but it can just be better at some of them. So there's the issue of permutations and specializations, especially in real-time shading, and that's actually my original background, where you have to generate numerous permutations, numerous variants of the same shader with complex design time logic and maybe simple runtime logic. There's the problem of low level of abstraction because some of the shading languages lack abstraction mechanisms. For example, GLSL doesn't have struct methods or templates. And then there's the concern of portability. And of course, well, we want portability between the different shading languages, but also between the specific applications, because each application requires its own specific API to write plugin shaders for it. Like, for example, Maya viewports may require one API, and Hydra Storm may require another. Then modularity is also not really solved in many of the specific platforms, so includes are not even a part of the GLSL standard, and linking barely works. So it would be nice to solve this on a higher level, independent of the target language. And then code reuse, I would put it this way: there is no STL for shaders, so there is no standard. Well, of course, there is Material X, but basically, well, what if you want to reuse some code in writing a deferred shading renderer or a tiled forward renderer? You usually end up just rewriting some code snippets from white papers. So it would be nice to have a library of generic algorithms, kind of like STL, that could be reusable in a variety of contexts. Here are the design principles that I followed while working on Metashade. So I wanted it to integrate into anything without asking for permission. So the host application shouldn't have to know that there is a Metashade. And that means that, well, the host app shouldn't require a host runtime library to link to. Metashade should be able to generate any code for any shader stage. It should be flexible enough to accommodate the specific APIs of the host applications. And all of that pretty much leads to the observation that we have to generate source code and not an intermediate representation because, well, that's the lowest common denominator. And of course, Metashade shouldn't require rewriting everything in Metashade. And then another major point in the design is that we should be able to interleave CodeGen code with arbitrary Python code so that we can integrate with the Python ecosystem, with pipeline scripts written in Python, and but also so that we can build abstractions on top of the basic CodeGen primitives. Next up, I wanted to introduce the concept of generators, which is central in Metashade. A generator is basically an object that models the semantics of the shader being generated. And we always create concrete generators, like a specific shader profile for HLSL, for example. But we can definitely have polymorphic CodeGen, like this generate function in the pseudocode that works on a generator without knowing what the underlying implementation is. Some implementation details explaining this unusual Python syntax. Basically, it's motivated by the fact that well, C-like languages have very different semantics from Python. So, for example, well, scoping works very differently, and typing works very differently. So, with statements model C-like scopes, operator overloading models, target expressions, getAttr and setAttr, which overload member access in Python. They're used to expose the target variables as members of the generator object, the sh dot pattern. And with this, we get complete control over all of the accesses to those variables, and we can enforce the C-like semantics on them. Some examples of how well the Python code would map onto target code. As you can see, we can generate comments, which wouldn't be possible with transpotting, for example. And some comparisons to the existing solutions. Of course, well, these solutions already address those challenges that I enumerated at the start of the presentation. So of course, well, the C preprocessor is still very popular, well, especially in real-time shading, both for portability and for metaprogramming. But well, Python is of course a much nicer programming language than the C preprocessor. Compared to generics and templates, there are lots of similarities, but one problem is that, like, for example, C++ templates are a pure functional language, and it's sometimes hard to reason about. With something like Metashade, we can have imperative metaprogramming. And also we can have metaprogramming independent of the target language. So for example, GLSL, which doesn't have any template or generic support, can still benefit. And then compared to shader graphs like Material X, of course, well, those are hugely useful, and Metashade is not trying to compete with those, but it can fill in the gaps. So for example, well, first of all, Material X and friends, they're really targeted at material authoring, but there is also the other piece of the puzzle, which is renderer implementation in, say, well, GPU renderers like Redshift. And Metashade can help with the implementation of CodeGen for the individual nodes, because, well, last time I checked, the individual code generators for Material X are pretty separate from each other, and there is not that much code reuse. And lastly, compared to transpiling, transpiling is the go-to solution for portability, and it works great in some scenarios. But well, Metashade offers a more of a top-down approach where we can use higher-level knowledge about the differences between targets to work around those differences. And lastly, I have to mention that there are other Python-based edsls for GPU programming, like NVIDIA Warp, Taichi, Numba, and OpenAI's Triton. But they are pretty different from Metashade in that they actually transpile a subset of Python. Well, they capture Python's AST with something like a function decorator, and then they transpile this Python AST to the target. Well, the syntax becomes nicer with this approach, but on the other hand, you can only support a subset of Python with this, and you can't mix this meta code with other Python code, so you miss out on metaprogramming opportunities. And all of these four actually only support compute targets and not something like vertex or pixel shaders. And that's pretty much it. Thank you guys for tuning in. Please consider checking out the repository, and let's talk about what applications or languages you would like to see supported with Metashade. And I do have to mention that Maxon is hiring, so you can check out this link as well. Thank you.